I wanted to just quick show you something that one of my classes did and explain some of the maybe common textbook definitions of looking at a confidence level. So what I did here was I had my students make a confidence interval for the proportion of black beads in a sample. So I poured a bunch of beads in. I did not tell them what the ratio of beads was. And I had them, basically put like a Dixie cup in and then count the number of black beads and number of white beads in the sample. Okay, so you can see the first person, 17 out of the 27 were black, 10 out of the 19, and so on. So then I had the students calculate their individual confidence interval for that. So, okay, the p hat is 17 divided by 27. Make the interval using the calculator. And then I had them graph those. So you can see their confidence intervals. Obviously, the bigger ones came from the smaller samples, and the smaller ones came from the larger samples, because larger sample leads to a little bit more accuracy. And after this was constructed, I said, okay, what proportion, knowing that I bought these in bags, so it's not like I bought a bag of 2,000 beads and poured it into this bucket, what ratio do you think the beads are actually there? And what they guessed was probably in here. It's probably in that 67%. And let me just show you, I have my little Amazon order. That is, in fact, the exact ratio. There are 6 black bags in there and 3 white bags in there, so a 2-to-1, or 2/3 of them are black. So they captured it. Okay, they were able to with their confidence intervals. But what I really wanted to do is draw your attention to this one. There are 20 up here. And this is not an accident. It really did work out. One interval didn't catch that 0.67. It was too low. All of the others did. So 19 out of 20, remember, is 0.95. So think about what confidence level means. If we conducted from this population a similar or the same sampling method and built intervals, 95% would catch the real proportion. And in fact, exactly 95% did. Finally, I wanted to talk about something pretty important, and that is how do we decide sample sizes? If you want to create a 95% confidence interval for the proportion of people at White Bear Lake Area High School South Campus who have a tattoo, how many people should I include in my sample if I wish to have a margin of no more than 0.03? Well, let me remind you of something we looked at yesterday. You should have somewhere printed out the formulas and tables you're going to be allowed to use on the AP exam. This is Roman numeral 3. It's the 3rd page, inferential statistics. Confidence interval is the statistic plus or minus the critical value multiplied by the standard deviation of statistic. And let me just remind you that this is the point estimate, and this is the margin of error. Now you notice here I have not been given a point estimate, and that's for a reason. It doesn't matter. All I care about is making the margin of error 0.03. So I should be setting this blue box, whatever, filling it in, equal to 0.03. Well, I know the standard deviation of my statistics, since I'm dealing with proportions, is this formula, and now I need a critical value that goes with 95%. So if you go and you look at the bottom of the bottom of table B in that same, you've got your formulas and tables, the critical values are down here. We wanted 95%. It is the one right above it, 1.960. We don't have to worry about the rest of the table quite yet. Okay, so let me draw up to that. 1.960 is the critical value. So what I now have is 1.96 multiplied by this standard deviation has to be equal to 0.03. Now, sometimes you're actually given a P, like use this as the proportion to start you off. You'll notice I didn't give you that. So you have to think, well, what would be a logical choice to use? The most logical choice, if you haven't been given a P, is 0.5. And there's two reasons. One, statistical method, or statistical reason is that's the break point between majority and minority. So, why not use it? It's a sound guess, 50-50. The mathematical reason is this will create the largest possible interval. 0.5 times 0.5 is 0.25. 0.6 times 0.4 is 0.24. 0.7 times 0.3 is 0.21. This is the maximum margin of error. So really, we'll probably achieve an even better margin of error than 0.03. But this ensures ensures that we will get the correct thing. Let me quickly run through the algebra here. Okay, so I would probably begin by dividing both sides by 1.96. So you've got 0.25 over n equals 0.03 divided by 1.96. Then I would probably square both sides. So now we've got 0.25 divided by n equals 0.03 over 1.96 squared. I would multiply both sides by n and then divide by this number here, this 0.03 over 1.96 squared. So in the end, let me go write it down here, n is going to be equal to 0.25 divided by 0.03 over 1.96 squared. So then we type that in. I get this answer. When I type it in, notice how I typed it. We must always, regardless of decimal, we must round up. So the answer here is 1,068 people. The reason we always round up is because going down would not achieve 0.03. We'd have a margin of error of just above 0.03. Rounding up actually gives us a lower margin of error than we even need. So if you've ever read a poll and thought, boy, that seems like a weird choice. Why would you sample 860 people? Why 1,700? It's because that is the sample size necessary to get the margin of error that the polling company desires.